Hello guys, it's the Med Dude, and today we're doing Edexcel IAL Physics Unit 2, January 2022. So let's begin. So we have question number 1. Which of the following units is equivalent to the volt? So we have the volt. So what equations are relevant to volt when we have J for energy, or also known as W. W is also known as the unit for power. So the equations we have for volt related to power and volt related to work is W equals QV, P equals IV. So to now find V, we need to do what? V equals W over Q. So the unit for this would be J over C, which is Coulomb minus 1. So that's one unit. The other unit we have is V equals P over I. That'll be watts over amps. So that'll be watt ampere minus 1. So let's see. So this is what? This is energy over time. That's power. So A is not it. Then we have power over time. This is a quantity that does not equate to anything. Then we have J Coulomb to the power minus 1, which is what we already have here. So we can say that the following units are equivalent is C. So C is the answer. Question number 2. So we have the de Broglie wavelength for a moving electron is 5.47 times 10 to the power minus 10 meters. Which of the following expressions gives the speed of the electrons in meters per second? So the equation for de Broglie wavelength is what? It's lambda equals Planck's constant over what? Over the momentum, right? Now we can simplify this even further. We can because we want the speed, and we know momentum is equal to what? Mass times velocity. And the mass is of what? The mass we're talking is about the electron. So mass of electron, which is given to us, is 9.11 times 10 to the power minus 31 kg. So let's see if we can rearrange this. So we have the lambda equal Planck's constant over mass times velocity. Now we want velocity on its own. So what should we do? We should bring it to where the lambda is, and we divide by lambda. So we will get V equals Planck's constant over m times lambda. Now let's see which of these are relevant. So velocity equals Planck's constant all over mass of electron times the de Broglie wavelength that's given to us. So we can rewrite the numbers instead of rewriting it again. We can say 6.63 times 10 to the power of negative 34. Okay. Then we have mass of electron, which is 9.11 times 10 to the power of minus 31 times by the de Broglie wavelength, which is 5.47 times 10 to the power of negative 10. And let's see the options now. So A, can A be it? We have 6.63, tick. We have 9.11, and we have 5.47. So A is the answer. All right. Now let's go on to question number 3. So the diagram shows a cell of EMF E and internal resistance R. The cell is connected in series with two resistors, R1 and R2. The potential difference across R1 is V1. The current in the circuit is I. Which of the following expressions is correct? So now they're talking about the EMF. The EMF is what? EMF is the total of all the voltages that are present. So which ones are there? So we have a voltage here, right? Then we have another voltage here. We can say it's I because it's V equals IR. V equals IR. So our total voltage will be what? It will be three terms. We will have I small r plus V1, which is this voltage over here, plus the second voltage, which is IR2. So we have three terms. So it's not A, not B, not C, because they all have two terms. Last one, let's see if we have the same term. So V1 is there, IR2 is there, and I small r is there. So our final answer is D. Let's move on to question number 4. So we have, as temperature increases, the resistance of the negative temperature coefficient thermistor changes. Which of the following best describes the reason for this change? So, to answer this, we need to first remember what are these thermistors made out of. These thermistors are made out of semiconductor materials. And why is this important? This is important because semiconductor materials, they release more conduction electrons as temperature goes up. As temperature goes up, resistance goes down, so more conduction electrons are being released. So let's look at the first one. So if the temperature increases, A, collisions between electrons and ions occur less frequently. That's not true, because where the temperature is increasing, then the collision should increase because they have more energy, right? So A is not the answer. B, more conduction electrons are released. So this, I explained that this could be the answer, right? So let's just say tick for now. Let's see the other two options. The ions in the thermistor vibrate less. The ions in the thermistor vibrate more. Now we're talking about what? We're talking about the resistance. Resistance is dependent on what? Resistance equals V over I. Can we simplify this in terms of electrons? Maybe we can. I equals Q over T, right? And Q is what? It's the number of electrons, so like NE over T. So this we can rearrange to substitute back into a VT over NE. Now, as we're increasing the number of electrons released, so as N increases, R decreases. So we know the conduction electron one is right. But what is R dependent on? These vibrations don't do anything to the resistance. Resistance does not change because of this. So we're left with B, and that's our answer. Let's move on to question number 5. Question 5 and 6 refer to the following information. Diagram shows diffraction of ray of light as it passes through three transparent substances L, M, and N. The speed of light in the three substances are VL, VM, and VN respectively. So we have a line, we have a ray of light that's passing through L. So this is clearly faster, then it slows down, then it's going to a faster medium again. So which of the following shows the relationship between VL, VM, and VN? So we just described it. We just said that this one is fast, this is slow, and because you can see that this slope is more steeper than the slope over here. So I'm going to compare them side by side. You can clearly see that this slope, this we call it Vn, this is VL, just the slope of the light. You can see that it's a bit faster, right? But it's not as slow as M. So we know that Vm is the slowest, so it should be at the very end. So Vn is not the slowest, Vm is the slowest, VL is not the slowest, VL is not the slowest. So by process of elimination, we should get B. But we can also figure it out if we just look at it saying that, oh, VL is the greatest speed, then we have Vn, then we have Vm. So we are sure about the last one and the first one, so we can easily conclude it's B. Now, next part says what? Question 6 says, which of the following could result in a ray of light undergoing total internal reflection? Total internal reflection. Okay. So, what does total internal reflection depend on? Depends on what? When you're going from a more dense optically medium to a less dense optically medium. Yeah. So we get what? So we can say over here that we know the velocities of L, M, and N, the mediums. We can say now N, which is the refractive index of N and N of M. This is because we know N equals C over V, and since we know that VL is the largest, so VL will be over here, this will be the largest, so N will be the smallest. So now we have this. The only way we can get total internal reflection is when it's going from the more dense material, so M to either N, M to either L, or N to either L. So we can't go from a less optically dense material to a more optically dense material and get total internal reflection. That's not how it will work. So these are our only possibilities. Let's see what they're talking about here. So they're saying light traveling from L to M. So L to M, we won't get total internal reflection. Then we have light traveling from L to N. We can see it's none of options here. Then we have M to L, which is correct, and N to M. Again, we can't go from here to here because it's more optically dense. We will not get TIR. So the only correct answer is C. Moving on to question number 7. The diagram shows how the displacement varies with distance along a stationary wire at 2 instances of time. So this is the displacement given to us. We have node, then another node, and then over here. Which of the following statements are correct? So we have points W and X are in antiphase. Points W and Y are in phase. Points X and Y are in phase. Points X and Z are in antiphase. So you can see, let's try to figure this out. So if we were to say, for example, that this is, let's say, one node over here. This is one node. I'm going to do the other node in another color. So these two nodes are adjacent, right? Because they're adjacent, all of the red line, I'm going to call it, that we have noted, is in antiphase with the blue line. Okay, so that means that W and X are in phase, right? And Y and Z are also in phase. So what are the options they give us? They tell you that W and X are in antiphase. No, because they're on the same node, same nodes, the same from here to here. So they are in phase. W and Y are not in phase because they're W and Y, if Y was here, then they'll be in phase. But because it's not, because it's on the other node, which has a trough of the negative max peak, we can say that they are in antiphase. So X and Y, same thing, antiphase, because the same one is W. Now X and Z, X is here, Z is on the adjacent node, so they are in antiphase. So D is our answer. Let's move on to question number 8. This is a standard question. The graph shows how current I varies with potential difference V for an electrical component. They give you the graph which component is represented by this graph? I've just shown a picture of a graph from the IAL textbook where you can see this is for a diode. So this is for a diode. Now for question number 9. So two wavelengths with wavelength lambda are produced by the same source. The waves travel different distances and then meet. At the point where they meet, the path difference between the two waves is lambda over 8. Which of the following is the phase difference in radians between the two waves? So we know that one wavelength is the same as traveling 2 pi. Now, if the path difference is lambda over 8, that means it should correspond to 2 pi over 8. So this should give us pi over 4 phase difference. So this is pi over 4. All right, let's move on to question number 10. So a light dependent resistor LDR and a fixed resistor are connected in a circuit as shown. So this is R, this is our LDR. The intensity of the light incident on the LDR is increased. Which of the following does not take place in the light as the light intensity is increased? So they're saying which of these are not happening. So let's see. So when the light intensity goes up, resistance goes down. I remember it as lights up, resistance down. So we know the resistance is going down. So because the resistance is going down, we can say what? That more conduction electrons are being released. More conduction electrons are being released. This means what? We know that the I equals Q over T, which is the same thing as number of electrons over time. If N is increasing and the time stays the same, that means that I is also increasing. So they said, which of these does not take place? This is taking place, so A is wrong. Then we have the potential difference across the fixed resistor increases on the fixed resistor, right? Now, because we have a constant electromotive force, if the resistance of this has gone down, then this must increase to give us the constant EMF, because we know V equals IR. This is V equals IR, right? Because we still need to have the same potential difference. So if this potential difference is going up, this potential difference must go down to give a constant EMF. Now let's look at C. The total power dissipated in the current decreases. Now we know that P can be represented in what? P can be represented in I squared R. And we know that the current is increasing. The current is increasing. So P must increase. So they're saying the total power dissipated in the current decreases. We're saying it increases. So this is correct because this does not take place. So C is correct. And the resistance of the LDR decreases. We already mentioned that lights up, resistance down. So this is obviously already wrong. So C is the only answer. Now let's move on to the structured questions. Question number 11. So we have a nichrome wire of length 0.45 meters has a cross-sectional area of 2.5 times 10 to the power of negative 7 meters squared. The resistance of the wire is 2 ohms. Calculate the resistivity of nichrome. Now, we need to first always write the formula down. So resistance equals rho L over A. We're trying to work out what rho is. So rho equals RA over L. Do we have everything given to us? Yes, we do. So we know the resistance is 2 times 2.5 times 10 to the power of negative 7 all over 0.45. So when we put this in the calculator, we got 2 times 2.5 times 10 to the power of negative 7 all over 0.45. We get 1.11 recurring times 10 to the power of negative 6 ohm meter. Now what do we round it to? We can see that this is to 1 decimal place, this is to 1 decimal place, and this is to 2 decimal places. We look at the lowest one, so that is 1 decimal place. So we round it to 1.1 times 10 to the power of negative 6 ohm meter. So that's our final answer over here. So what do you get the marks for? We get the marks for saying the final answer and for using rho equals R equals rho L over A. So now we're in part B. A potential difference is supplied. A potential difference of 3 volts is applied across the nichrome wire. Calculate the drift velocity of the conduction electrons in the nichrome wire. Number of conduction electron per meter cubed at 9 times 10 to the power of 28 meters to the power minus 3. So as soon as we see drift velocity, we are looking at the formula I equals NQVA. They have given us N. We know Q is 1.6 times 10 to the power of negative 16 C, right? Negative 19 C. Do we know V? No, we don't. We're trying to work it out. Do we know A? A we know is what? Is given to us from the previous question, which is, you can see, cross-sectional area. So it's 2.5 times 10 to the power of negative 7 meters squared. So we have that. Now, what's missing? We also don't know I. We don't know I. How can we work out I? They've given us potential difference. We only know V equals IR. I equals V over R. So 3 over 2 ohms, because 2 we got from here. We will get 1.5 amps. So now we just have to rearrange. So V equals I over, so what's remaining? So NQ and A is the remaining. So NQ and A. So we get 1.5 all over N. N is, they've given us 9 times 10 to the power of 28 times the charge, which is 1.6 times 10 to the power of negative 19, multiplied by the area, which is 2.5 times 10 to the power of negative 7. So putting this to the calculator, what do we get? We get velocity, drift velocity equals, so we get 4.166 recurring times 10 to the power of negative 4 meters per second. Again, what should we round to? You can see that the lowest amount of significant figures are 2 or 1 decimal place. So we should round it to 1 decimal place. So we will get 4.2 times 10 to the power of negative 4. Don't forget the units, meters per second minus 1. Meters second minus 1. So what are the marks we get for this question? So we get 1 mark for using the equation I equals NQVA. So just writing the formula down is very important. You might just get 1 mark. Then we have to work out I, we use V equals IR, so that's the 2nd mark. And 3rd mark is to get the final answer, combining the 2 equations together. Alright. Now let's move on to question part C. A student suggests that the drift velocity will double if the length of the wire used in circuit is halved. Comment on this suggestion. So they're saying that the L nu, which is the length, is now a half of the current L, right? How will this affect the drift velocity? Now we know that drift velocity is affected by this because V equals I over NQVA. And I is affected by V equals IR. So V equals IR. You can see I is affected directly by the resistance. And we know that resistance equals rho L over A. So our new R will become what? Our new resistance of this new length of wire will just be rho L over A, and then we have the half, so I'm going to call it a half. Right? Which is the same thing as saying it's half of the resistance we had previously. So our V equals IR, or I equals V over R. I equals V over R. Our new R is what? Is half R. So we can say there are new, so I equals V over R over 2, which is the same thing as saying what? Same thing as saying 2V over R. So that's the same thing as 2 of the, so I new, 2 of the original. So the current is what? Current is doubling. So we can say, so you can write all this calculation. The current doubles. Current doubles. This means, so because the current doubling, we know that 2I now equals NQVA. So V equals 2 multiplied by I all over NQVA. So now you can see it's increasing by a factor of 2. So V will double. And what can we say about the suggestion? V will double. So suggestion is correct. So a correct suggestion. So now we have question, so 11 part C. So we get the marks for saying that the current will be affected, and then will be double, and we one crucial thing is that we need to state on the comment on this, we have to comment on the suggestion, which is it's a correct suggestion. That's our third mark. All right, let's move on to question number 12. Rolled steel joints are used in the constructions of buildings as shown. So these are rolled steel joints. The strength of an RSJ is greatly reduced if there are air gaps within the steel. Ultrasound is used to detect any air gaps in the RSJ. Pulses of ultrasounds are sent by a transducer, we can see in the diagram. Transducer into an RSJ as shown. Any returning ultrasound is detected by the transducer. So the ultrasound wave is sent. There's an air gap, so you can imagine that it probably reflects back somehow, either goes here, then reflects somewhere else, and at the end comes back transducer, as opposed to if there was no air gap, it would go straight down and then back up again. So any returning ultrasound is detected by the transducer. Question says what? Explain how this arrangement can be used to show whether the RSJ contains an air gap or it doesn't contain an air gap. Now, the key word here is that they're saying explain how this arrangement can be used to show. So you have to explain as if this was an experimental procedure. Experimental procedure. So what can we say? So we just talked about it. We said that if the pulses are sent, right? As the pulses are sent, they will return in some reflected form. It will reflect somehow, or it will reflect from here, for example, and it will go up, or it will reflect again somehow, reflect from here. At the end, it will end up where? To the transducer. So the first thing we have to tell them, because they're very picky with the words, is that we have to state that the pulses that are sent return to the transducer via reflection. This is from the boundaries. Now, if you were to say bounce back, it's they don't consider it. So using bounce is not specific enough. So bounced is not specific enough. So you need to make sure you mention the word reflection of these pulses. So now, how can we tell if there are air gaps within the RSJ? Now, for example, if the transducer sends an ultrasound pulse here, and then it reflects back, for example, as opposed to if there was no air gap, for example, if there was no air gap, it would go straight through, wouldn't it? It would go all the way down, and then all the way back up again. right? So we can say that the time taken, so we can talk about the time here. We can say that first measure the time taken for pulses to return without the presence of an air gap. So this will give us the time taken for the pink lines, the reflections. Let's first measure the time taken for the pulses to return without the air gap. Then, if there are air gaps present, for example, what will happen? So this time be smaller, right? This time I'm going to call this capital T. So capital T will be smaller than small t, right? Much smaller because the distance traveled is much less, right? Compared to if there was no air gap. So we can say if there are any air gaps within the RSJ, then the time taken will be less than the time taken if there was no air gap, right? Then the time taken if there was no air gap. If there were no air gaps. No air gaps. That's it, right? So let's look at the four points that we can mention. So the one point is that we mentioned that pulses are sent to the transducer via reflection. So that's the key word here, and that gives you the 1 mark. Then we have to state that we are measuring the time, so we can compare it with some value. So 1 mark for saying the pulses are reflected back to the transducer. 2nd mark for saying that we should measure the time. 3rd mark for saying that if there are any air gaps, then the time will be less than if there were no air gaps. That's our 3rd and 4th mark. All right. And this is because, so we can expand on this further. We can say this is because what we mentioned before, that the distance traveled is less. This is because less distance is traveled by the pulse. Less distance traveled by the pulse if air gap is present. If gap is present. All right. So 3rd mark, I'm going to do it in another color. So 3rd mark for saying if there's already a gap, the time taken will be less. Then what? Then we're comparing it to the time taken if there were no air gaps. 3rd and 4th mark. Let's go on to part B. Ultrasound is a sound wave with a frequency greater than 20 kilohertz. The frequency of ultrasound is used by the transducer is 5 megahertz. Explain why a much higher frequency than 20 kilohertz is needed in this method. So first, let's talk about the differences between the 20K and the 5 megahertz. Clearly, you can see the one has a greater frequency, right, than the other one. So we're talking about what? Higher frequency. So to show this, we must explain that V equals F lambda, and then what? We explain what? Because V is still the same, right? What's happening with the frequency? Since frequency is increasing, then what should happen? Lambda must decrease, resulting in what? Resulting in smaller wavelengths. So that's the first key thing we need to note. Now, why is it better in this case? Why is it better for us to use smaller wavelengths? That's the question. Why is it better for us to use smaller wavelengths? Now, it's better for us. I'll give you two words. The two words are resolution and penetration. Now, what does this mean? So, for resolution, this is what? This is when we have smaller wavelength. So, smaller wavelengths allow for higher resolution imagery. So, it increases what? It increases the ability to locate small details within a material. So, the resolution, we can say this is what? Ability to locate small details within a material. So within a material. Now, if we have smaller wavelengths, this allows for higher resolution imagery. So you can say smaller wavelength allows for what? Allows for higher resolution imagery. So this means what? We can locate the air gaps, the smaller air gaps, much more easily, right? Now, penetration means that it can go further within the material. If let's say it's a very, very big material and it goes very deep, we can say the penetration that it allows, the smaller wavelengths can travel further. We can say it allows for what? Better detection. So high resolution imagery and better detection. So those are the 3 points. So we have to state that what? It leads to smaller wavelength because frequency is increasing. Then we can say it allows for higher resolution imagery, and this is when what? This is the ability to locate small detail within a material. So that's what higher resolution will increase. This will increase this ability. And penetration, we said in adds for, we can say wavelength allows us to get better detection. So that's our third mark. So 1, 2, and 3. All right. Now let's go to question number 13. In the early 20th century, observations of the photoelectric effect demonstrated that light behaves as a particle. Explain how observations from the photoelectric effect demonstrate the particle nature of light. Now, this is a very repeated question from previous past paper, but we need to make sure that we are mentioning the demonstration of the particle nature. We are not trying to disprove, so we are not disproving the wave aspect, wave nature. That's not what we are doing. We are trying to demonstrate the particle nature. So anything that, if you mention anything about electrons being excited, so excited, falling down, exciting, dropping down, which results in releasing photons, is not relevant. So all of this will give you a 0. This is a 6-mark question. So we need to be very careful on what we're talking about. So the first thing we need to remember when we're demonstrating the particle nature is that we can quantify the energy transfer. So we can say we can observe that the energy transfer is quantized, right? It's quantifiable. So we can say quantized, and which can be seen. Which equation do we have that relates this? We have E equals HF. So we can now mention this, which can be seen through E equals HF. Now, because it's a particle nature, we need to talk about each individual photon interacting with electron individually, right? Individually. Because particles, right? So we have to mention it where each photon interacts with an individual electron. Okay. Now the second part. So that's the first thing we mentioned, that's quantized, and we mentioned where it has to be individual because we're trying to show the particle nature. Secondly, so now we're going to talk about what? We're going to talk about the threshold frequency and when electrons are being released. So we can say, secondly, electrons are emitted, and electrons are emitted anyways, but we need to talk about how fast they're emitted. They're emitted instantaneously as or when exposed to light above the threshold frequency. All right. Now, so that's another thing we mentioned. To further demonstrate, we can talk about what? We can talk about if the frequency is increasing, then we can talk about our EK, right? We can talk about our kinetic energy, and we can talk about light intensity, whether it affects it or not. So we have to further demonstrate the particle nature. We can say what? We can say that as frequency increases, so we know that EK equals HF minus phi. We know that the energy of each, so energy of each, or we should say rather individual photon increases, whereas increasing the intensity of the light does not increase the EK. Doesn't increase EK of photons. But what does it do? If we are increasing the intensity of the light, we still get more incident photon, don't we? So it's not a result of the increase in energy, it's rather the number of photons that are present increases, that are present on the metal surface increases, not because of the EK. So let's see what we talked about here. So first we talked about what? We talked about quantization, right? So that's one thing. And then we mentioned that this quantization is for an individual interaction between a photon and electron, that's two. And thirdly, these photons are being released instantaneously. There is no wait. There is no, in a wave, a nature of light, you can see they're all emitted slowly but surely, but all of them are emitted. But in this, we're showing that the electrons are emitted instantaneously, right? Then, when we expose them to light above a threshold frequency, there is a marking point for stating that it's above the threshold frequency. That's our fourth point. Then to further demonstrate, we mentioned that the frequency increases because that's related to wave. If we were to increase the frequency, that something shouldn't happen to the wave nature. We now mention because we increase the frequency, EK increases, but when we increase the light, nothing happens. So that's our fifth. So fifth of the energy, and sixth for mentioning that doesn't change anything when we increase the intensity of light. All right, now we can move on to question number 4, recorded 14. So we have a laser, a diffraction grating, and a screen, a setup as shown. The laser emits a monochromatic light. So this is of a single wavelength or a single set of wavelengths. Laser, diffraction grating, and then we have the screen. When the laser is switched on, a series of bright dots are seen on the screen. So now we have a diagram. The diagram below shows the position of the central dot at O. The next bright dot appears at position X. The diffraction grating has 450 lines per millimeter. All right. The question asks us what? Determine the wavelength of the light from the laser. So let's see if we can do this. So determine the wavelength from the light from the laser. So the formula we use is what? Is n lambda equals d sine theta. Correct? Okay. This is the formula that we use. Now let's work out these individual values. So they're talking about what? So this is the first bright dot. The next bright dot appears at position X. So this is when what? When n equals 1. This is the first bright dot appearing after the central one, central maxima. So we can say what? We can say, so we know that n equals 1, right? Do we know d? D is what? This is the distance between the diffraction gratings, right? So how do we work this out? We know that per 1 millimeter, there are 450 lines, right? 1 millimeter has 450 lines. So the D would be 1 millimeter divided by 450. So that's the same thing as saying what? So we can do it over here. This will be 1 millimeter converted into meters is 10 times the power negative 3. So we have 10 times 10 to the power negative 3 all over 450. This gives us what? In the calculator, this gives us what? We can just keep it as it is for now because it's there. Meters. What about sine theta? Now we have the triangle. The angle is between X and the diffraction grating. So this is our theta. Now we want sine theta. Sine theta we know is what? Sine theta is opposite over hypotenuse. So we have our opposite over here and hypotenuse over here. Now to find hypotenuse, we can do what? We can do a square, a, b, and c. We can do a right angle triangle. This is a right angle triangle, so we can do Pythagoras theorem to find c. So let's work it out. So that'll be what? A squared plus b squared equals c squared. So in this particular case, we will have what? So we'll have 1.69 squared plus b. B is 0.5. The distance between O and x, 0.5 squared, equals c squared, which is hypotenuse squared. So now we can just square root both of them. So we can get rid of this now. This will give us our hypotenuse. So now let's calculate. So square root of 1.69 squared plus 0.5 squared gives us 1.76. It's a big decimal, so it keeps on going. So don't change this value. All right, keep it in the calculator. So sine theta is what? It's opposite. It's opposite over hypotenuse. So opposite we know is 0.5. 0.5 all over 1.76 and a lengthy decimal. So now we have everything we need. So lambda equals what? D sine theta all over n. So now all we have to do is substitute the values. So we have 1 times 10 to the power of negative 3, which is d, over 450, multiplied by sine theta, which is this. So 0.5 all over 1.76 decimal. And n is what? N we know is 1. Right. So we get what? So 1 times 10 to the power of negative 3 all over 450 multiplied by 0.5 over 1.76 and keeps on going is 6.304 times 10 to the power of negative 7 meters. Now is this the correct rounding? Let's check something. So we have what? We have 1.690 meters, 0.5, and we have 450. So you can see 450 is under two significant figures. So we can say it's 6.3 times 10 to the power of negative 7 meters. So where are the marks here? So this is the answer. Where are the marks here? Let's check. So 1 mark for getting the answer, obviously. Then we have 1 mark for using this equation. So it's very important to just write down the equation. Then we have to work out d, right? That's the 2nd mark. And 3rd mark is to find what sine theta was. All right. Let's move on to part B. Part B says what? Explain why a series of bright dots is seen on the screen. So in general, why do we get the bright dots? Right? This is why. Why do we get this? This is because I have a diagram over here to show. So this is due to what? This is due to what? Constructive interference. And then it's so the bright. So let's call these the bright dots. It's followed by darkness and then another bright dot, followed by darkness, then another bright dot. So the bright dots are what? Are because of constructive interference. The darkness is because of what? Destructive interference. Right. So what can we say? So we can say because I've explained over here, so we have waves from different. So this is waves from different slits are meeting at this point to give you constructive interference. So we can say similarly waves, because waves traveling from different slits. So for example, over here, so we have the diffraction grating. So let's say it's over here. It's over here. Go from here to x, for example, and another one here. Let's do it in purple. It goes from here all the way here. So you can see that the waves coming from the diffraction grating, right? It's coming from the diffraction grating, from different slits from the diffraction grating, but they're what? They're constructive interference is happening, right? To give us what? To give us a bright dot, right? The bright dot. So what should we say? We can say, so because waves traveling from different slits, right? From different slits, so from different slits meet, and then what happens? What happens? We get what? And constructive interference takes place. All right. When does constructive interference happens? This is very obvious. We need to say what? We need to mention phase. Why? Because this is in phase, we get the bright dots, and destructive is out of phase. That's why we get darkness, right? So what should we say? Constructive interference take place. This is when waves are in phase. So what are the 3 marks? So we got 1 mark for saying waves from different slits meet, right? And because of this, constructive interference takes place, and this is when waves are in phase. All right, so that's our 3 marks: 1, 2, and 3. Now, what does it say? Part C. The laser is replaced by a source producing parallel beam of white light. So just what would now be observed on the screen. So for those who may have not seen this experiment, this is what the maximum looks like. So for example, this is our beam of white light. I will link another video showing this in a practical. So the beam of white light, this is the beam of white light that's being shown. So now that we have seen this, right, we can say what? So we would see, so what would be now observed? So now let's go back. This was O, right? This was O. This was the central dot of the same monochromatic light, right? So in this case, because we don't have the monochromatic light anymore, we have a bright white light, we can say that what? We see a bright white dot at 0 or O, which is, so this is our new O. And what's beside it? What do we see beside it? Don't say rainbow. Do not say rainbow. Say rainbow. They awarded marks for rainbow, but it was discouraged as it's still not that relevant. But because it was a poorly answered question, they gave marks. So what should we say? We should say what? We should say, and on either side of it, we see the spectrum. So this is the spectrum. And on either side, the visible spectrum is seen. So 1 mark for saying bright white dot, 1 mark for saying either side of, and we see visible spectrum. All right. Now we have question number 15. So a student investigated stationary waves on a string using the apparatus shown. So we have a vibrator, we have a pulley, and we have hanging masses. So the frequency f of the vibrator was adjusted until a stationary wave was formed with a node at each end. This was repeated for various stationary waves on the string. A meter rule was used to measure the distance between the adjacent nodes on the string. The resolution of the meter rule is 1 millimeter, but the measurements were recorded to the nearest 0.5 centimeters. Again, for those who may have not seen the practical, so we have our, let me see if I can get, so this is where, so we have 2 adjacent nodes. So this is the practical. So the distance we're trying to measure is from here to here, right? And because the string is oscillating in real time, back and forth, it's very hard to get this d accurately. So we can just say that it's very hard to find the exact d. So all we can say is it's difficult because it's oscillating. It's difficult to get exact d or exact distance d as the string is vibrating. String is vibrating. All right. So that's our 1 mark. The student plotted a graph of d against 1 over f. So meter against 1 over f. So 1 over f is what? T equals 1 over f. So this is essentially time, by the way, just so we can remember in maybe we need it. So this is the graph, okay. Then it says determine the total mass of the hanging masses used in the investigation. Mass per unit length is given to us. So this is mass per unit length. Because they've given us mass per unit length, right, we can use the formula that's on the end of this paper, which is V equals T over mass per unit length. So we know that somehow we need to use this to find the total mass somehow. All right, let's go back to the hanging masses. Let's look at them in detail. So we have the hanging masses, right? So what's happening? There is weight over here, right? Weight equals mg, and that's supported by what? The tension of the what? Of the string, right? So we know that the tension that is mentioned in our first equation over here, the T here can be represented by what? T can be represented by W, which is represented by mg. So we can now find the mass somehow if we rearrange to find T in the equation. So we can say T tension is equal to weight of the hanging masses. Okay, so because they're equal, we know that T equals mg. So we know that. Okay, that's good. So we now know T to some capacity. That's good. Now, what about V? Now we saw before, didn't we, that we can just go back here. Distance over time, or 1 over f, is what? Distance over time gives us what? Velocity. And that's what? That's the slope, isn't it? That's the slope. So we don't need to use 2 points. We can just use a point. So let's go here and see which of these points are easiest to work with. So we can see what? We can see that at 0, we can just go to the very edge. We see that 0.8. At 0.8, we are at 2.7 meters. Okay, that's good. So now we can say that slope equals distance over 1 over f, and we know that T equals 1 over f. So distance over time, which gives us velocity. So that's therefore now we know distance over time is what? Is 2 is but will this give us velocity? Let's track back a little bit. We know what? We know that the velocity is for what? It's for 1 lambda, isn't it? It's for 1 wavelength traveled. So now we need to find what? The time or the distance. You can see if this is d, then this will also be d. This will give us the entire wavelength, right? So what? So what should we do now with this? So we know that v will be 2d over t, which is the same thing as saying 2 times the slope. And in this case, which is 2 times, so let's take d over here as 2.7, and the time is given to us as 0.8. So 0.08. So 2 times 2.7 divided by 0.08 gives us, so V equals 67.5 meters per second, or meters ms to the power minus 1. Now let's rearrange this formula to give us T. So this will be what? V squared equals T over mass per unit length. So T equals what? V squared mass per unit length. And we know that T equals mg. So mg equals V squared mass per unit length. So m equals V squared mass per unit length all over g. So now what do? We just substitute what we know. So do we know the velocity? Yes, we do. It's 67.5 squared multiplied by what? Multiplied by mass per unit length, which is 4.5 times 10 to the power of negative 4 all over 9.81. So this gives us what? So 67.5 squared multiplied by 4.5 times 10 to the power of negative 4 divided by 9.81. The calculator gives us 0.20900 kilogram. So let's see what we should do. So this is to two significant figures. This is so we should stick with that. So we should 0.21 kilogram. So what are the marks for this question? All right. So this is the final answer. Well, let's look at the marks that we get. So 1 mark for getting the answer, obviously. So there is 1 mark for understanding that tension equals weight of the hanging masses. That's 1 mark. 1 mark for using just the equation. Just putting down the equation gives us 1 mark. 1 mark already. Then understanding that we need to calculate the slope, and then understanding that distance is, or lambda is 2d, which we calculated. We spoke about it, but we didn't write it down. But we did it here, so you get 1 mark for that. So that's our 5 marks. Next, the string was replaced. So the string is now replaced with one that had twice of mu. The length of the string have not changed, so they're the same. Add a line to the graph to show how d varied with 1 over f. Now you would think that we are just going to draw it. No, we need to find out what the slope is going to look like. So we know the v equals t over mu. Now we have a new mu. Now it's v equals root over t over 2 mu. I want to take this 2 out. If I take it out, what happens? If we take the 2 out, it becomes a half. And because we're taking it out of the square root, we still have to square root it. So it's t over mu, like this. So this is what? Let's put this in the calculator. Square root of 1 over 2 is same thing as 1 over square root 2, which is root 2 over 2. Now this is what in the calculator is 0.70. It keeps on going. So we're going to stick with 0.7. So v equals 0.7 t over mu. This means what? That the slope must be 0.7% or 0.7 times the current slope we have. Right? So let's go back. Now we took this value at 2.7. So now let's take 2.7 multiplied by 0.7. This gives us 1.9. So we now need to draw a line. So where's 1.9? This is 2. This is 1.9. So we draw a line from 0 all the way to this point. So this is why we're exact, and we should get both marks. So 1 mark for the line and 1 mark for understanding that we need to use 0.7 of the slope. Let's move on to question number 16. So now, this is a very standard question. We have light is a transverse wave, right? Describe the difference between a transverse wave and a longitudinal wave. So a very standard answer is for transverse waves, oscillations are perpendicular. Perpendicular. So this is just the symbol. Perpendicular to the direction of travel. But for longitudinal, so that's our one mark. So now for second one, longitudinal waves, we get oscillations are parallel to the direction of travel. To the direction of travel. So one mark for the longitudinal, one mark for the transverse, and this is our answer. So one mark for this, and another mark for this. Alright, now part B says what? Part B says there are two prisms, A and B, made from different types of glass, are placed in contact as shown. An incident ray of light enters prism A. So this is the incident ray going at a 90 degrees. So it's perpendicular. So it goes straight through. Let's go down. So state why the incident ray does not change direction as it enters prism A. Alright. So we can say, what can we say? We can say that we just talked about it. We just said that it's perpendicular to the prism, so it goes directly through. So we can say incident ray is perpendicular, so directly goes through. It's only one mark, so you don't need to think much about it. Let's go to part B, or II. The refractive index of glass prism B is greater than the refractive index of glass in prism A. So N of B is greater than N of A. Alright, so this is this is optically denser prism or denser material, which is this one. So now the question says, when the ray of light reaches the boundary between the prism, some light is reflected, some is refracted. Complete the diagram to show the two paths taken by the reflected and refracted light until they have returned to the air. Alright, so let's go back. So they're saying that this line is being refracted and reflected at some point from here, right? So first let's draw the normal. So let's draw the normal. So this is our normal, right? Always good to draw normals. It helps us understand what's going on. Alright, so I'm going to do the reflected ray in blue. So first, let's see. So let's say it's reflected. So it's reflected here. So it reaches the prism in air. Now, it could either refract further, right? It could either refract from here, or what? It could totally internally reflect, right? That's a possibility as well. So either of these possibilities are correct. You can either go with this one or this one, but not both. Let's go with one of them, because you only need to show one line, right? One pathway. So TIR is also fine, is correct, and refraction outside is also fine. And because you can see that air is 1, this will be faster. It's less dense material. All right. Now let's look at the ray that leaves, that goes in. We know that prism B is more dense than prism A. So what should happen we should get what? It should slow down, right? It should slow down, correct? It should slow down. So it should slow down. Then, because reaching air again, it should come faster again. It should come faster again. So, speeds up. So, this is the refracted ray, right? So that's the possibility. So we get 1 mark for what? So I'm going to do it in maybe pink. So we got 1 mark for slowing down, 1 mark for going faster as it released, 1 mark for reflection, and 1 mark for, so either of these, or it's like you can, either of them, you can get a 1 mark. Because it's not stated and we don't know the angle of refraction for this prism. We have no idea. So either of these scenarios are correct. Let's go to part III. Part III says, calculate the angle of refraction as this ray of light travels across the boundary between prism A and prism B. So what are we talking about? They're talking about this angle here. So what are they talking about? They're trying to find out this refraction angle, or theta 2, or because it's of the other medium. So let's go back. They've given us n of A, n of B, and they're trying to work out what the angle of refraction is, or let's call it, let's say. So the equation is what? n1 sine theta 1. We know n equals n2 sine theta 2. Do we know the angles? Let's see. We know this is 60 degrees. If this is 60 degrees and this is a right angle triangle, this is going to be 30 degrees. And if this is 30 degrees and this is a right angle triangle, this will be 60 degrees. And if this is 60 degrees, then this will also be, this will be 30 degrees as well. So let's try it. So this will be n1. n1 is what? n1 is of the glass, right? n1 is equal to na, and nb is equal to nb. Theta 1 is equal to 30 degrees, and theta 2 is our theta r, which is we're trying to find. So now let's substitute what we have. So we have 1.4 sine 30 equals 1.55 sine theta r. Let's rearrange to get sine theta r on its own. So sine theta r equals 1.4 sine 30 divided by 1.55. Alright, good. Now what should we do? We should take the inverse. So theta r will be sine inverse of this exact same thing. So we can just duplicate it instead of writing it again. So we get what? So 1.4 sine 30 over 1.55, and now we take the sine inverse. It's 26.847 degrees, and this, the level of accuracy is usually to just 1. So let's just keep it to 27 degrees. So angle of refraction is 27 degrees. So what are the 1 marks? 3 marks. So we got 1 mark for getting the answer, 1 mark for inputting the variables and putting sine 30 as theta, and 1 mark for just putting the formula. So just putting the formula gives us a lot of marks. Next, so part C says what? So the light emerging from prism B, so light emerging from prism B is observed through a polarizing filter. The polarizing filter is rotated gradually. The light is transmitted by the filter varies in intensity. Explain how this observation demonstrates the light waves are transverse. Alright, so first thing we need to remember is the light is emerging from prism B. Alright, so the light that emerging from prism B, either polarized or not. Because if it is, then we should get varying intensity. If it's not, then obviously we won't get it. So we need to state the obvious, and we need to state that light leaving from prism. B is polarized. So that's our 1 mark. Mentioning it's polarized. Since rotating, the filters produces varying intensity. This means that hence the light waves are, and then we'd say the obvious, transverse, since only these types of waves can be polarized. These types of waves can be polarized. So 1 mark for saying that it's produced is polarized because it produces varying intensity. 2nd mark is stating that the light waves are transverse because these are the only types of waves that can be polarized. So now we have question number 17. A student has set up the circuit shown. So we have 12 volts, 4 volts, 3 and 6. Calculate the number of electrons passing point X each second. So they're asking for what? They're asking for number of electrons. They're asking for number of electrons. Do we know the number of electrons? We don't. Let's see if we can find this out, right? Is there something we can do here? Is there something going on here? Do we know anything? All we know is V. We know R. This is also R, and this is also another R, right? The number of electrons means that we're talking about the current being current. We were talking about the charges that are passing each second, right? We know that current is what? Is Q rate of change of charge over time, right? We know that Q equals what? Is IT. Do we know T? T equals 1 second, right? This is right. And charge is equal to what? It's the number of electrons multiplied by the charge, the 1.6 times 10 to the power of negative 19 coulombs, right? So Q is equal to what? Is equal to NE times IT. So number of electrons is what? IT over E. Do we know what T is? We know T equals 1. We know E equals, which is the charge, equals what? 1.6 times 10 to the power of negative 19. But we don't know I. So let's try to work out what I is at this point. To do that, let's first work out the I for the circuit. So I'll say I total, right? So what is it? It's V equals IR, right? And this is R total and V total, right? So this is 12 equals I multiplied by RT. RT is what? R total is what? It's 4, right? This is 4 plus. Now we need to find out the resistance for these two. This is what? It's actually the inverse of 1 over 3 plus 1 over 6. It's the inverse of this. So RT is equal to what? 4 plus. So a third plus a sixth is a half. And then it's the inverse of this. So the R total is what? Is inverse of a half is just 2. So it's 4 plus 2. So R total equals 6. So I equals I circuit equals what? V over R total, which is 12 over 6, which is what? 2 amps. So there are 2 amps flowing here into the circuit, and then what happens? So now we have parallel. This is a parallel series, right? This is a parallel circuit now. The resistance is in parallel. So we have 2 I1 and I2. So where does the current usually favor? So we know the more current will favor which? Will favor the least resistant path. And because of this, now let's look at the ratio between the two. This is what? This is 3 and this is 6. So this will what will happen? So we know this is 1/3. This is 1/3. This is 1/9. This is 6/9. Right? So one takeaway. So let me see. Let me show you the ratio. So because the resistance is less by a factor of 3, we can say that 2/3 will be here. 2/3 amps, or I, should I call it? I will be here. And 1/3 I of the circuit will be here. Now because of this, we can say what? That I at X will be 1/3 multiplied by 2, which is 2/3. So N equals 2/3 multiplied by 1 each second, and 1.6 times 10 to the power of negative 619. This gives us 4.16 recurring times 10 to the power of 18 electrons per second. So then we can round this to 4.2 times 10 to the power of 18. So now let's look at this. What are the marks? So obviously 1 mark for the answer. Then we have 1 mark for getting that IX is 2/3 amps over here. So 1 mark for this. 1 mark for calculating the circuit current. 1 mark for calculating the resistance. The parallel resistance is 1 mark. The total resistance is 1 mark. So 1, 2, 3, 4, and 5. And then understanding that when you define N, it's Q equals IT. So that's 1 mark as well. 1, 2, 3, 4, 5. Yeah, 1, 2, 3, 1, 2, 3, 4, 5. And using I equals Q over T. 6. That's 6 mark. Alright. Part B. Another resistor Y is added to the circuit as shown. So this is another resistor over here. The student wrote the following statement. When resistor Y is added, the resistance of the parallel section increases. The resistance of the whole circuit increases, and so by I squared R, the power dissipated by the whole circuit also increases. So the question says, evaluate the student's statement. Okay. So before we do this, let's check whether the first thing he says is correct. So he said the resistance increases, right? So R total is what? 4 plus, so 1/3 plus Y plus 1/6. This we can rewrite to give you 3 plus Y, and this is 6, like we did before. So now we can use the formula and we can inverse it. And let's see, so now it's R total is what? 4 plus, so 6 plus 3 plus Y all over 6 times 3 plus Y. Inverse, this is 4 plus, so this becomes the numerator becomes 9 plus Y all over 6 multiplied by 3 plus Y. Inverse, so R total is 4 plus 6, 3 plus y all over 9 plus y. Now to see if it increases, we know that our total was what last time? It was 6 ohms. Yes? Now let's take any value for y. Let's say y equals 2, for example. 2 ohms. So what should happen to the R resistor? Let's substitute. So 4 plus 6, 3 plus 2 over 9 plus 2. So this is 30 over 11. 4 plus 30 over 11 gives us 6.7 more decimals ohms. So what happens? So we can say that resistance does increase. Resistance does increase. But we also know that the current changes as well, right? Because we worked earlier that current changes as well. So this is not a good way of finding the power, right? We can use another formula. Another formula is what? P equals V squared over R. Because we know V is constant. That's not going to change. V is constant. So we can use P equals V squared over R, right? And since R increases, P equals V squared over R increases, power would be less, right? So is the student correct in stating that? No, it's not. So yes, resistance does increase. So student is incorrect in his statement. So what are the marks? So just stating student is incorrect gives you 1 mark. So these are the very obvious things where we have to state the things. We know that since R is increased, power has to decrease. So this is 1 mark. Stating that V is constant, and that's why we're using P equals V squared over R. And the 4th mark is to state that R has increased. So that's our 4 marks. So now we have question number 18. Sirius A is the brightest star in the night sky and is mostly composed of hydrogen. When light from Sirius A passes through the hydrogen in the outer layers of the star, some light is absorbed. This causes electrons in the hydrogen to be excited. The diagram shows an electron being excited from negative 3.4 electron volts to 1.5 electron volts level. So what does it say next? So this is the diagram. So wavelengths of different colors of visible light are shown in the table below. Violet, blue, all the way to red. Deduce the color of the visible light that's caused the electron transition shown in the diagram. So because we can't, so this is the difference. So because this is E1, this is E1, and this is E2. So what should we do? We need to find delta energy, and because we can't work with electron volts, we have to convert it later. So delta E equals, in this case, E1 minus E2, which is what? So E1 is minus 1.5. So minus 1.5, take away, minus 3.4, 3.4, and this gives us what? This gives us 1.9 electron volts. So 1.9 electron volts. Because we can't work with electron volts, we have to now change it to 1.9 multiplied by 1.6 times 10 to the power of negative 19. So 1.9 to 1.6, this gives us 3.04 times 10 to the power of negative 19, and this is in joules. Now because we now know E, we can now do what? We can do E equals HF, right? Now, will this help us? Yeah, it will, because we need the wavelength, right? Now we need a formula for wavelength and frequency. The only formula that's available to us is what? V equals F lambda, and since we are in space, so this will be in a vacuum, so this will be lambda equals V over F or C over F. C is the speed of light, which is 3 times 10 to the power of 8. All right. So what should we do here? We need to find lambda. We have f. So now we should first actually rearrange to find v over lambda. So c over lambda. So we should substitute this into this equation. So we have E equals hc over lambda. And now we can rearrange to find lambda. So this will give us lambda equal hc over the energy. So now we just have to put in the values, substitute in the values. So now what's Planck's constant? It's 6.63 multiplied by 10 to the power of negative 34 multiplied by c, which is 3 times 10 to the power of 8 meters per second, and we know the energy, which is 1.9 electron volt, which is 3.04 multiplied by 10 to the power of negative 19. So putting this in the calculator, what do we get? We get 6.54 times 10 to the power of negative 7 meters. To convert it into nanometers, we multiply by 10 to the power of negative 10 to the power of 9. So this gives us 654 nanometers. So let's see where this lies. So 380, nope. Blue, nope. Green, 570, 590, no. 620, nope. So we're left with red because it's 654. It's within the range. So we can say that it falls under. So we can say the color of light. So the color of visible light is red. Visible light is red. All right. So 1 mark for getting 1 mark for converting and getting 1.9 electron volts. 1 mark for using E equals HF. 1 mark for getting the nanometers, and 1 mark for stating that it's red. All right, so that's part A done. Let's go to part B. A light year is the distance traveled by a light in 1 year. Sirius A is 8.6 light years away from Earth. The intensity of radiation is received on Earth is 1.17 times 10 to the power of negative 7. Then we have calculate the power of Sirius A. So first, let's look at the equation. The equation is what? It's I equals intensity equals power over area. So power equals what? Equals IA. Now, do we know I? We know I. We know. Do we know A? A is what? Is 4 pi times r squared. Because this is a sphere, right? So 4 pi r squared is the surface area. So what's R? R is the distance. So R equals distance between what? Between Sirius, so Sirius A, and Earth. So what's that distance? So that distance is 8.6 light years. Whoa, light years. So what should we do with this, right? So we know that what? To find distance is what? We know the V equals S over T, right? So S equals VT. And since we're in space, it's in a vacuum, so S equals C times T, right? So R is 8.6 light years. So let's see if we can find this out. So it becomes 8.6 light years. Well, that's the time, right? That's the time. That's the time. So now what? So now to find time is 8.6 light years. So that's how much distance travel? That's C times T. C is 3 times 10 to the power 8. That gives us C. That's C done. Now what about the time? A year has how many days? It has 365 days. And each of those days have 24 hours. And each hour consists of 60 minutes. And each minute is worth 60 seconds. Alright? So when we multiply all this, what do we get? Let's see. So 8.6 multiplied by 3 times 8, 10 to the power 8 times 365 times 24 times 60 times 60. This gives us 8.136 times 10 to the power of 16. So now, we can get power equals I multiplied by 4 pi r squared. So P equals, so I is what? 1.17 multiplied by 10 to the power of negative 7 multiplied by 4 pi. And R is what? R is 8.136 times 10 to the power of 16 squared. So let's now input this into the calculator. We will get 1.17 times 10 to the power of negative 7 times 4 pi times r squared, which is 8.136 times 10 to the power of 16 squared. This gives us 9.733 times 10 to the power of 27 watts. So 9.733 times 10 to the power of 27 watts. So now we can simplify this because this is in, look, 3 significant figures. We can now convert it to 3 significant figures. So 9.73 times 10 to the power of 27 watts. So what are the marks here? So 1 mark for the answer, obviously. What else? 1 mark for calculating the distance of the light years. 1 mark for remembering that the surface area is 4 pi r squared. And 1 mark just for using the formula. Just for using this formula, we get a mark. So always write down the formula. Next, this is the last question, part C. When hydrogen gas is excited in the laboratory, only certain wavelengths of light are emitted. Explain why. This is very standard. All we have to say that photons which are released only have certain energy levels, and this is true because if we go back up, this is what we mean by it only has certain energy levels. Like only certain, there is no minus 5.6 eV volt now, is there? Only certain energy levels. Therefore only certain differences in energy levels are possible. So 1 mark for stating that they only have certain energy levels. So certain energy levels, that's 1 mark. 1 mark for saying there's only certain possible combinations of these energy levels. So this is why they're released. So this is why we get only certain wavelengths. So 1 mark here, 1 mark here. And this is the end of the paper. And I'll see you next time.